Started the recording. Okay, so still not opened up. So as soon as this PowerPoint opens, we will start doing the review of moment distribution. But in the meantime, let's just recap that we were looking at moment redistribution in continuous beams. So what is that? We said that if you use only elastic analysis to design a beam, then we are or to estimate the design strength of a continuous beam, if we use only elastic analysis, we are underestimating the actual moment capacity of the beam, because it is an indeterminate structure, provided that there is enough ductility at the joints. There is possibility of plastic hinges developing at certain joints, especially the negative moment regions, and then that will cause a slight decrease in the negative moments and a slight increase in the positive moments. And because of this, the code allows us to reduce the amount of negative reinforcement that we provide in continuous beams. So this is what we were discussing, and we were going through the PCA document. And then we were about to start a review of moment distribution, and we stopped for some reason, but we will finish it now. Okay, so there is a caveat. It's just sometimes that we get confused with the terminology. Moment redistribution is used to make a more economical design for continuous reinforced concrete beams, taking into account of additional load capacity due to formation of plastic hinges. But moment distribution moment distribution is a structural analysis method used for indeterminate beams. So very briefly, we will recap moment distribution. Okay, so we said mainly we are using these two cases. I think these two are enough to solve most of the continuous beam problems. One is propped cantilever and one is simply supported. When we apply a concentrated moment at one end, then the relationship between applied moment and angle of rotation at that end is m equals 4 times EI by L theta for propped cantilever. At the other end, of course, there is no rotation since it is a cantilever, but there is a moment m over 2 transferred to that end because of this applied moment m. For the simply supported, the relationship between moment and angle of rotation at that end is m is 3 EI by L theta. And if we have theta is the rotation at this end, we will have theta over 2 at the other end. Now, these two results we can derive easily using any method of deflection and rotation, like moment area method or slope deflection method, or any of those. Now, that is the concept we use to analyze uh, yeah, not to distribute any concentrated moment applied at a joint. So at any structural joint, if we apply concentrated moment M, that moment will be carried in some proportion by each of these members which are connected at that joint. Now, what is that proportion? It is in proportion to their stiffness. So whoever is the stiffest, he will carry the most moment and so on. So for each of those we checked, okay, this is prop cantilever, 4 EI by whatever length. Then this one again prop cantilever, this one simply supported. Like that we assign the stiffness and then we divide by the least common multiple for everyone so that we get fractional stiffness values. So you will notice that all of those should add up to 1. 2 over 21, 8 over 21, 3 over 21, and again 8 over 21. Yeah, so that adds up to 1. So we took an example problem. We just started. So here is a continuous beam, and there are some. It has 2 spans, and we will start by putting in the relative stiffness. So at this point, so we have propped cantilever at either end. So it will be 4 EI by L for either end. So we said that, okay, it's 4 EI. I is moment of inertia is I for the left span. EI by length is 5. For the right span, moment of inertia. So moment of inertia is 3I and length is 7.5. So then we reduced it finally to 1 and 2. So 1 over 3, 2 over 3. That is the relative stiffness. Now let's write the fixed end moments. So we can use a table of fixed end moments for standard cases. Let me just open. Just give me 1 second. I have a small thing. Okay. So this is the table of fixed end moments. You might remember it from your structural analysis courses. So concentrated load at midspan, we have PL by 8 is the fixed end moment at either end. So let's use that. Concentrated force, and then we have P is 100 kilonewton, L is 5 meter. So we have P L by 8, 62.5 kilonewton meter. So let's put that. So we said at the joint, clockwise is positive. So So this will be negative. This will be positive. And for this is uniformly distributed load and fixed. Uniformly distributed load, fixed is WL square by 12. Again, this also many of you may remember, it's frequently used. W is 20, L is 7.5, WL square by 12 is 93.75. So positive, negative. Okay, so the next step is okay, also carryover moments. Okay, so how much is the carryover? Okay, we have not yet applied. So 1 second. So now we do the moment distribution. Moment distribution. So we have negative or positive 93.75 minus 62.5. So we have excess moment of positive 31.25 at this joint. So I need to apply here. Negative 31.25. If I apply negative 31.25 at this joint, now 1/3 of that will be carried by the left span, and 2/3 will be carried by the right span. So if I apply negative 31.25, then negative 10.42 will go here, and 2/3 of 31.25. Negative 20.833 will go here. Okay, so because of this, we can put the carryover moment as well in this step. Since I'm applying here a moment of negative 10.42 for this span, out of that, half of it will go to this side, that is negative 5.2. And half of this will go to this side, 10.42. So now let's do once more. Now let's check once more what is the total unbalanced moments at this joint. So on the on the left side, we have negative 62.5, negative 10.42, that is negative 72.92. And on the right side, we have
That would be 72.917.
yes, so positive 72.92. So we already got equal and opposite moments at this joint. So we don't have any more balance. And this one adds up to 62.5 minus 5.21, 57.29.
And the last one is negative 104.2.
Okay.
Yeah.
0.2. Okay. Thank you very much, Mercy. So since we have only one continuous joint here, and at that joint, the moment is already balanced. There is no excess moment. So we already ended our calculation. So you can see that the advantage of moment distribution with respect to some other methods, like maybe matrix method, or you don't need to solve any system of equations here. That's why it was so popular. It's still very popular, even after so many computer programs and all have come into the picture. It's still very popular. Okay. So let's take one more example.
Dr. Nickton, excuse me, can you
yes.
please repeat it? The process that you did that solution, moment distribution?
Yes.
Just the general.
No, yes, sure. Just one moment. So in the first step, we got the absolute stiffnesses of the spans at this joint. For rotation at this joint, what is the stiffness of the left span? What is the stiffness of the right span? Then we reduce that to absolute fraction that adds up to 1. So 1/3 and 2/3. Then we calculated the fixed end moments according to, usually many of them we can find using the standard values in a table like those. And so those are our fixed end moments. Now at every joint, if the answer is already right, that means we should not have any unbalanced moment at a continuous support, because for example, this is a continuous support. By moment equilibrium, whatever moment is on this side should be equal and opposite to the moment on the other side. But right now we have an unbalanced moment. After we wrote the fixed end moments, we have an unbalanced moment, which we expect because fixed end moment is for the case like that, that's also fixed, but in reality that's not fixed. So essentially what we are doing is we imagine first that it is fixed, and then we say, hey, this is not fixed, so how to make it unfixed? I need to apply equal and opposite moment to whatever moment is unbalanced here. So here we had moment of 62.5 kilonewton meter on this side, and on this side we had moment of 90.75 kilonewton meter. So totally we had a clockwise moment of 31.25. That was the unbalanced moment at this joint. But we said, hey, we want to make it balanced. So we apply counterclockwise of 31.25 at this joint. So that means negative 31.25. And like we saw here, if we apply any external concentrated moment at a joint, that will get distributed in proportion to the relative stiffness. So here our relative stiffness is 1/3 for the left span, 2/3 for the right span. So that 31 point. Yes.
Yes. So that moment of 62.5 and 93.75, you get it by looking at fixed end moment.
Yes. So if we see this left span, the case is concentrated load at mid span, right? That's the case, right? So I will look up that case. First one, right? Concentrated load at mid span. Then the fixed end moments are PL by 8, PL by 8, right? So P is 100 kilonewton, L is 5 meter. So if I do 100 times 5 by 8, I got 62.5, right? And direction is at the support or at the joint, clockwise is positive. So we can follow, I mean, in different textbooks, it might be different, but we said that, hey, this is a very good book for us. See, if you remember, I said it's a very, very old book, very small book, but very useful. So we are following his sign convention. Maybe in some books it might be a bit different, but mostly it should be same.
Can you upload these two files on eLearn?
Yes, I think it is there. Let me go and see. Okay, I just need to do one thing. Like usually all the books are in introduction or in getting started. Oh, it's not there. You're right. Okay, well, let me put right now. Okay, it is uploading. And now you can see here, moment at the end of a member is considered positive when it is in counterclockwise, anti-clockwise, and for joint clockwise. Okay, that's the same convention we are also following. Let's take another example. Okay, so let's take this one.
And how about the right-hand side? Will be the one with uniform distributed load?
Oh, okay. Sorry, yes, this is uniformly distributed load. So for that one, we use this case, uniformly distributed load W. So when you have uniformly distributed load, fixed end moment at either end is WL square by 12. So if we do W is 20 kilonewton per meter, 20 times L square 7.5 square by 12, we got 93.7. Yes, sorry, I got somewhere else. Yes. So is it clear, Bryson? Okay.
Yes.
So let's pick. Sorry, go ahead.
For the second line, the moment will be distributed
Yes,
equal
that's
to
the
left and
moment.
right.
The moment will be distributed. Can you say again?
Will be distributed half to the left and right.
Oh, no, not half. See, it will be distributed in the ratio of the relative stiffnesses. So, see, what is the relative stiffness? 1/3 and 2/3, right?
Yeah.
So, if we apply negative 31.25 here, 1/3 of that will go to the left span, 2/3 will go to the right span. So it will be distributed in the ratio of the relative stiffness, not half and half.
So I'm asking the one from dot 5.21 and negative 10.42.
Yeah. That is carryover moment, because you see when you apply moment here, then half is carried over to the fixed end, right? That's why.
Sure. Okay.
Okay.
And for the last line?
Yeah. So last line, we are again trying to see what is the balance. So we have done one moment distribution and carryover, and now we are again trying to see the balance. So we got equal already, so 0, no more unbalanced moment, right? So we don't need to balance anymore. We are done, right?
Yeah, sure. Thank you.
Okay. Okay, let's do one more. Let me just do one thing in a moment, and then we will do one more example.
Thank you, Bryson, for asking that. I was kind of confused how he got 62 and 93.
Oh, yeah, you're welcome. So, Messi,
Hmm?
how did you get this 72.92?
2.92?
72.92?
Oh,
last line?
you just add it up. You just add the negative 62 minus 10.42. The last part is just adding them up.
Oh,
Yeah.
thank you. So if it could have been not balanced again, you're supposed to take 1/3 to the left and 2/3 for the right. Am I correct?
Can you repeat that?
If the last line, the moment could have not been balanced, you are supposed to take again 1/3 to the left and 2/3 for the right. Am I correct? Or let's say maybe the last line could have been the total 72.92
We
to the
can
right. Maybe the left hand could have not be balanced.
we can try to see even taking again, see.
Yeah, I think if they would not be balanced, then you would repeat the process again, multiplying it times 1/3 and 2/3.
But it gives you the same thing because like if you're trying to take another 1/3, you still get 31.25 of 1/3 is 10.42. You'd get the same you still get the same like result as 10.42 and 20.8. So I think that's when you know it's the deadline too.
Mhm.
Okay. Good. Thank you so much.
You're welcome.
Yes, so let's do one more example now. We can do this one. Okay, let's do this one. Just a second, I will come back. Let's do this one now.
Class is still on.
Sorry. So yes, let's do this one. Uh, so for this one, we have 1, 2, 3 continuous supports. So let's just make okay. So we can do it in one way to avoid any further issue from this overhang. We can just put this way that because for this particular overhang, it is clear if we make a cut to the left of this support, we will have 50 times 3, 150 kilonewton meter moment here. So let's just put that one. So here 40. So this should be the value here. It cannot change. Let's write the relative stiffnesses. Okay, now this one is a free end. So for free end, relative stiffness is infinity because everything will come to the right side. Left side is empty, nothing is going to go there. So it's infinity. For this, we have on left side simply supported, and so this is going to be 3 times EI by L. So 3 times I divided by L. So 3 EI by 6 meter. On right side, we need to take this as fixed. So it's going to be 4 times EI by L is 4. So this is 1/2, this is 1. So this is 1 and 2. So we will get 1/3, 2/3. Here, now we have on left side 4 times EI by 4. On right side, again 4 times EI by 4. So it is just half and half, both are equal. And this end is fixed and so 0. Okay. Now we can write our fixed end moment. Okay, actually here it is, we will still need to assume fixed and then release it. So yeah, so we will put here 80, 80. So let's go check the fixed end moment cases. We have 2 equally spaced loads. Sorry, small mistake. So if everything comes here, this will be 1, not infinity. Okay. So here is our case, 2 equally spaced loads PP. Fixed end moments are 2PL by 9, 2PL by 9. So we have P is 80 and L should be the total L, 6 meters. So P is 80 times 6 by 9, 53.33. So dip, negative, and here there is nothing. So 0, 0. Here 40 uniformly distributed. So that should be this case WL square by 12. So 40 times 4 square by 12. Also 53.33. Negative. Now we will do distribution and balancing. This is relative stiffness. This is fixed end moment. Now we will do one distribution and carry over. Just give me another moment. I'll be back. Okay, so should be okay. Okay, now moment is distribution. So see the first one, we have positive 53.33, but there we need, what we need is only the 150 kilometer meter uh, on the other side. On therefore on on this side we we should be having also 150. So at at this location we need to apply uh, like we have a negative 150 and positive 153.33. So the net is negative 96.67. So we need to apply here positive 96.67. Okay. Now, and here we have negative 53.33 total difference. So we should apply positive 53.33. So let's do that. So positive 53.33, 1/3 of that will go to the left, 17.78. And 2/3 of that will go to the right, so 35.55. And here we have positive 55.33, they will go half and half. So that is 26.67 negative, negative. And here it is this itself is the right value. We don't need to do anything. So we just put a 0 because at this fixed end, it is already a fixed end, so we don't need to change anything. Now I have done the moment distribution here. Now our balance and moment distribution. Now carry over, let me write in the next line. Let's write carry over here. So I have positive 96.67 here. So out of that, sorry, just a second. Okay, so 96.67, so half of that should get carried over to this side. So plus 48.33. Then carry over from here to now this side is a free end, but yes, this side is free end, so there is no carryover here. Now on this side, we have negative 26.67 here, so half of that will get carried over here. Negative 13.34. And let's put this step as carryover. 35.55. Half of that will get carried over. Positive 17.78. And this is 0, so no carryover. This is negative 26.67. So half of that will get carried over. 13.34. Okay, so now let's see what are our values. So this is a total. Let me just check. Should be fine. Yes, should be okay now. Now let's total here is 150. Now let's total here. $12.78 positive. Here.
That would be 22.2.
Oh, thank you. 22.21 positive. Here. I'm sorry. This step must be negative. Yeah, no, it's okay. It's okay. Yes, okay. This side is negative 26.67, positive 17.78, negative 8.89. This side is positive.
Be 26.67.
Yes. This side is negative
39.
66.67. Okay. So let's check. Okay, we have positive 150, so That's what we need, so we don't need to do anything there. So here is 0. Here we have total of 12.78 plus 22.21 plus 34.99. So we need to apply minus 34.99. So negative of that will go here. So we are applying negative 34.99, and 1/3 will go to the left, 2/3 to the right. And here we have positive 17.78. So we need to apply half and half. So negative 8.89, negative 8.89. This one is nothing. So it's balance, moment distribution.
Can you explain the sign you used here?
Whoops. Yes. So here in the total row, we have 150 here, which it should be 150. So nothing, no need to balance any moment. So 0. Here we have positive 12.78, positive 22.21. So that total to 78, 22.21 to 34.99. So we need to apply negative 34.99 to balance that.
Okay.
And okay. So now let's do. Let's do the carryover step. Okay, so now we applied 0 here. So 0 carryover here. We applied negative 11.66, but no carryover. We applied negative 23.33, half of that will carry over. So that is negative 11.67. We applied negative 8.89, half of that will carry over. So negative 4.45.
And then 0 and negative
then
4.4.
Yes. So now let's do. Let's move this. We are getting close. So
Can you please explain the last line?
this one, yes. So this is negative 11.66, but this side is pinned, so nothing transfers. Then this is 0, so nothing transfers. Then this negative 23.33, half of it is transferred, I mean carried over. Negative 8.89, half is carried over. This negative 8.89, half is carried over, 0, nothing, right? This is carryover step. Now let's come one more step. Okay, so now let's do again total. So now previous one was 12.78 minus 11.66. 1.12. This is 22.21 minus 23.33 minus 4.45. Negative 5.57.
And
Then this one, sorry.
the next one should be negative 29.45.
Negative 29.45. Okay, thank you.
And then that one is 17.78.
Positive, yes. And this one is negative
71.12.
yes. And this is just 0 again. Okay, so now you can see we have much smaller moment to balance. Negative 5.57, positive 1.12, negative 4.45. So put 1/3 of that to this side. So we have negative 1.48 on this side.
2.96.
Right, negative 2.697 something. Then here we have negative 29.45 and positive 17.78, negative 11.67, half on each side, negative, so positive 5.84. These two should be positive. Positive 5.84 and positive 5.84. And now next will be the carryovers. So 1.48, nothing carries over here, nothing here. This one positive 5.84 by 2. 2.92 carried over here. Positive. This is carryover. This is 2.97 by 2, 1.49. Here 5.84 by 2, 2.92 and 0. Okay, so now we can see that totals are getting smaller. Yes, Bryson.
Why you didn't carry over 4.48?
Oh, you mean this positive 1.48?
No, the positive 4.48 on the second line from the bottom.
Maybe I forgot. You mean this one?
That's not 4. I think you put
That is
positive.
positive 1.48 because this end is pinned, right? Nothing will carry over here.
I think it just looks like a 4 with the plus sign.
Sorry. Let me... Now, what we want to do is you accept the totals, accept the line of total line, we add up everything, okay? So, just a second. Just a second.
And what is the reason of not carrying the moment to the pin support?
So if we have pin support on this side and you apply moment M on this side, nothing is carried over here, right? Because it's pin. Only if it is fixed, half of it is carried. Okay. That's why, yeah. Just a second with the totaling now. Just a second. So this is a totaling step. Okay, so what we do now, accept the totaling steps, we add up everything, okay? So here we have positive 150 because we still have to make it till we don't have any difference, but we are very small numbers, so we can stop here because of time. Now we add up all these, negative 53.33, positive 17.78, excuse me, positive 48.33, negative 11.66, positive 1.48, or 2.6. And here, 0, 35.55, minus 13.34, minus 23.33, minus 4.45, plus 2.97, plus 2.92, 0.32. And here, negative 26.67, positive 17.78, negative 8.89, negative 11.67, positive 5.84, positive 1.49, negative 22.12, on this side 53.33, minus 26.67, minus 8.89, plus 5.84, positive 23.61. And here, negative 53.33, negative 13.34, negative 4.45, positive 2.9, negative 68.2.
So when we were taking the second total, we didn't add from the beginning, right? We only added from the first total. We added from the first total up to.
Yeah, we skipped this total line. The totaling lines were just the reference for us to balance the moment. We don't count those. We add everything except those totaling lines.
But
Okay.
the one we did right now is from the very top.
Yeah, top to bottom, everything except the totaling lines.
Okay.
So you can see almost we are balanced. Here there is some small difference, 2.6.32, negative 22, positive 23. Okay, almost balanced. If we do some more, they will be exactly equal. Okay, let's check now. It's a bit off.
I think I know why it's a bit off. Can you go?
This number, our first fixed end moments number was not okay. 80, let me see here. BP. Oh, this is 2 PL by 9. PL by 9. Okay, so I think I did PL by 9. 80 times 6 by 9. Yeah, it should be 1 or something. Okay. Okay, that's fine. Let's just, since we need to go back to the.
Can you just write the first step?
Yeah,
like,
yeah,
can you write
sure.
the 106? Okay.
Sure. We will. Okay, let's just do it as quickly as we can. Then that way.
We don't have to go through the whole thing. Maybe just the first line.
Okay, we do just a few steps till we get to some small number.
Okay.
Let's just do a few steps. Let's do one thing. Let's make the slide a bit bigger. Okay, just a moment.
Should have asked how he got the first step again. We need to figure it out.
Go. Let's go.
Mercy, I think from the book he uploaded where he gets the fixed end moments, it was written 2PL over.
Yeah, I know. Remember earlier Bryson was asking how he got it. We should have asked for this one too. I
No,
really don't know
I'm
how he
saying,
got it.
like,
I
yeah,
just
yeah, when he comes back, we can, but just right now, he showed like he went back to the book to see where he got wrong
oh,
because
he didn't do it earlier.
he did PL over 6 instead of 2PL over 6. So, like, the value we got, we were supposed to multiply it by 2. So, like, that's why he got 53.33, and back in the book, it's 106.
Yeah,
Yeah, I think
for
that.
the first questions, I thought, with the first questions, I know how he got it, so I thought he got it the same place, but I didn't know where he got it. Like I
Okay.
didn't ask him.
I think he goes through the book where to get the fixed end moments very fast. But
Yeah,
I think when you're going through it yourself, like, because
yeah,
he uploaded the book in eLearn, right?
yeah. I'm not sure it was loading. I'm not sure if he submitted. I mean, after a load,
Oh,
you have to submit it to be fully uploaded. So let me check.
Yeah, I was trying to find it on eLearn.
He didn't submit it. It was loading and then he just left. So we need to remind him.
Okay.
Press submit. Yeah.
Oh, that sounds good. So once you care out the moment, the one from the left, you go to the right, and the one from the right go to the left.
Yeah, it's crisscross.
Oh, okay. That's good.
kind of like the one that goes, like, if you get the one at the left, when it goes to the right, it becomes a negative, or how does it work?
So like if you're taking if you're doing the cross, the one that's on the fixed, it just becomes 0. But if you're in the middle, if you're taking the one that's on the left to the right, if the ratio is saying 1/3, you have to take 1/3 of it. And then if it's saying, half, you have to take half of it when you're taking it to the opposite, the diagonal side.
Oh, okay.
Yeah, you have to follow the ratio on the top when you're taking it to, but if it's on the very dead fixed side, it just becomes 0.
Okay.
Is that at fixed moment kill half of the moment?
I'm sorry, what, Bryson?
At fixed end, is it killing half of the moment?
At the beginning, but then you let it go at the end. I mean, he was trying to put it as infinity, but he was like, let's just carry it until, half of the step, and then at the end it just becomes 0 because it's fixed anyway.
Thank you.
If you remember when he started doing it, he put it as infinity. Then he was like,
Mhm.
let's just leave it as it is, and then because at the end it's just gonna become 0 anyway.
Yeah, sure. Thank you.
Okay, sorry, I have to do something. Uh, let's make it bigger. Okay, let's just redo that one. So,
Dr. Nathan, can you check on
yes.
the uploading of the book to
Yes,
eLearn?
yes.
Thank you.
Yes. Yeah, still uploading. Maybe it's a bit big, that's why. Okay, but it should be finished. Okay, so there is one more change we have to do here. Let me tell you that too. So here, we had moment of 150 kilonewton meter. Our fixed moment that should have been 2p by 9. I put p by 9, that messed that up. PL, I put this PL by 9 instead of 2PL by 9, but we are going to fix it right now. So let's put relative stiffnesses. This one was okay. 3 EI by 6 and so on and so forth. So 1, 1/3, 2/3, half, half, and 0. That was okay. Yeah. Okay. Now, at the fixed end moment stage, we need to make a small change. That is over here. Over here, we are taking this as a pinned end. So therefore, when we apply 80-80, that is for fixed case. So we have to, since this end is not, we are not taking as fixed, we are taking it as pinned. It is better that we adjust in the first step itself. Instead of fixed, we take it for fixed pin. So let's do that in a separate case and then put those numbers. That will be easier. So we have for fixed 80 kilonewton, 80 kilonewton, 6 meter. For this case, we have 2 PL by 9. Uh, 2 times 80 by 80.6 by 9, 106.67. But now we want this to be pinned. So therefore, we should apply here negative 106.67 on this side. So that means and half of that will carry over here. So 53.3334. Now this should be this side is 160 and this side is nothing, no force, okay, no movement. So this is the proper fixed end moment for us. So that's why, so now we have a 150 on this side. We have 0 here and we have a
106.7.
negative 150 here. Sorry.
Oh, I was saying it should be 106.7 on the 1/3, under the 1/3.
No, it will be negative 160 now. Because see, we are taking, we already accounted for this case that this is a pin. Okay, so for this case where 80-80 fixed, For this case, fixed end moments are 106.67, 106.67. Okay.
Okay.
But when we already release this to become pin, then this becomes 160, this becomes 0. Okay.
Okay.
So we start with here 0, negative 150 this side, and negative 160 here, and here is nothing. So 0, 0. So here is this was okay. 53 positive, negative 53.33. So this was relative stiffness. This is fixed moment. Now we do our balance. So we have negative 150, 0. So we need to apply positive 150, but everything will go here. And nothing will go there.
Negative 160 moment.
Oh, sorry, yes. Sorry, can you say again? Yes.
Can you repeat for the
Where
160
we get
moment?
160, yes. So this is fixed, right? But our case, we already took this side as prop cantilever. That's what we are considering here, right?
Yeah, sure.
So if this is fixed and also this side fixed, then it is negative, then it is 106.67, 106.67. But for us, we already said we made this into pin. So we need to remove this 106.67 for us, right? So if we apply in the opposite direction 106.67, half of that will carry over. Now, if we do this plus this, then we get our case, which is what we need, right? This is 106.67 and 53.34, so 160.
Okay, okay. Thank you.
Sure. So this is negative 160, 0. So we need to apply positive 160. So 1/3 of that will go there. So positive 53.33 will go here. And 2/3 of that will go. So positive 106.67 will go here. Then here is positive 53.33. So we need to apply negative 53.33. So half of that negative 26.67 will go here. Half of that will go here. And this is negative. This will remain same. So we are not applying anything. So we just keep it as 0. We don't need to balance anything. Then carry over.
So, Dr. Nathan, there should be 53.33 or 160?
Just a second. Carry. Where did you say?
At that, can you go to slide number 12?
Oh, okay.
Maybe 160 or 53 something.
No, they both are clockwise, right? So 106.67 plus 53.34, 160.
Because are in the same direction?
Yeah.
Okay. That makes sense. Thank you.
So let's do the carryover now. So we have positive 150 here. So half of that will get carried over. So positive 75 will get carried over. Here, nothing will get carried over, it's pinned. Here, 106, half of it will get carried over. Negative 26.67, half of it will get carried over. And here, half of this will get carried over. Here is 0. Okay, so that's fine. Okay, now let's just check. Okay, what did we apply? We balanced this one, then we carried over this one. Now, we have 75 minus 13.35 here. Positive 61.65. So we have to balance that. Here, nothing to balance. So 0, so we don't balance anything. Here, positive 61.65. So we need to apply negative 61.65. 1/3 of that to the left.
20.55.
Yes, so negative 20.55 to the left. And to the right.
41 point negative, I mean.
Yeah, negative. Yes, negative.
Negative 41.1.
Okay, negative 41. Okay. Here we have 53.33 and 0. So we need to. Here must be negative. This step negative. So this should be negative. Okay. Yes, now it's fine. Yeah, it's fine. So 53.33, and we need to apply negative. So therefore,
how are you checking? Like, how did you know that was supposed to be negative 13?
Because from this one, half of it will get carried over here. So half of negative 26.67 is negative 13.3.
Yeah, but did you see that something will be unbalanced when you're adding them?
Yes. So now unbalanced is because this side is positive 75, this side is negative 13.35. So we have unbalanced of 75 minus 13.35, that is positive 61.65. So I'm putting in negative 61.65 in this step.
Okay.
So balance with 75.
I'm sorry?
You put negative so as to balance with this 75?
So when he was adding 75, when he was doing 75 minus 13.35, he got positive 61. So he's doing the next step negative to balance with the 61. But if the 61 was negative, the next step will be positive, right?
Yes.
Okay.
Yes, exactly, Mercy. Yeah, it's exactly as Mercy said.
This is like the chemistry balancing equation thing.
Oh, kind of. Oh, I didn't think of that. Yes, it is. It is. It is. Here, 53.330. So, so we need to apply negative 53.33. That means half and half. Excuse me. We need to apply negative 26.67. Negative 26.67. Here is fixed end, so no need to do anything. So that's the balancing step. Now we do carryover again. So now we have zero, so this side nothing, this side negative 20.55, so this is prop spin, so nothing. Then this side is negative 13.33. This side is negative 20.55. Negative 20.55. This side is nothing. This side is negative 13.33. This is the carryover. Now we have here zero. We have negative 13.33, so we need to apply positive 13.33. 1/3 of that is positive 4.44. Positive 8.88. Here we have negative 20.55, so we need to apply positive of that. So positive 10.28, positive 10.28. And here is nothing. So that's the balance step. Okay, so now we have carryover step. So nothing carries over here, nothing carries over here. Here 10.28 over 2, 5.14 carried over here. And 8.88 over 2, 4.44 carried over here. Here nothing. Here 5.14 carried over. And we have 5.14 now. So that's the carryover. So we have 0 here, so positive 5.14, So put negative 1.71 here, and 2/3 negative 3.43 here. This is positive 4.44, so put negative 2.22 here, negative 2.22 here, and here nothing. So let's do the last carryover step is going to be quite small. So after that we will stop. This is the balancing. 0 here, 0 here. Negative 1.11. Negative 1.72. And here nothing. Here negative 1.1. Okay, so now let's just do the total. Since we are already at very small numbers. So we have this side total negative 150, this side total positive 150, this side total negative 160, plus, see, this time I skipped the totaling step because it's anyway only the carryover, so that's easier. So just add up everything, negative 160, positive 53.33, positive 75, negative 20.55, positive 4.44, negative 1.71, negative 49.49. Here we add all these, 106.67, negative 13.35, negative 41.1, negative 13.33, positive 8.88, positive 5.14, negative 3.43, negative 1.1, positive 48.37. See, we have a bit of difference still because we haven't gone all the way. When we go all the way, both sides are very tiny numbers, you will get exactly same. Negative 26.67, positive 53.33, negative 26.67, negative 20.55, positive 10.28, positive 4.44, negative 2.22, negative 1.72, negative 9.78. And right side 53.33, negative 26.67, negative 26.67, positive 10.28, negative 2.22, 8.05. Yeah, it is still, we have to balance a bit, that's fine. Negative 53.33, negative 13.33, negative 13.33, positive 5.14, negative 1.11, negative 75.96. Okay, so you can see relatively the continuous supports, the right moment and left moment are almost balancing each other. We have a bit still, we know how to do it. Okay, so let's check the book upload. Done. Book upload is done now.
So as the book, you uploaded, did you also upload right here the PDF file?
The fixed end moment. Fixed end moment. Yeah, that should take only a second. That's a very small file. Let me do right now. Now both are uploaded. Okay, so now I think we are okay with, so you can see we almost, so he did a few extra steps, one extra step than us, so he got quite close, but we are also almost same, close. Okay, so now I hope this moment distribution is not mystery, right? It's clear, right?
Yeah, it is.
Okay. Okay, so now let's see how we are doing it for moment redistribution. Okay. So first thing is that we have different, whenever we have continuous beam, okay, there is a point here, important point. Last time we discussed, but maybe we want to revisit that once more. Okay, and that point is that of moment envelopes. Yes, so come here. Arrangement of live load. See, this is a very important arrangement of live load. This is a very important point here. What this is saying is that, let me just explain in a very brief way. So, see here, supposing I have continuous span. Something maybe like that. So it will be there in every box frame, right? So the span will be like there are columns and then there are many beams in between them. So continuous span is very common in box frame. Now, we need to design every span for maximum possible negative moments and maximum possible positive moments, right? So how, when and how that will happen? Of course, from ASCE 710, you remember there are so many load combinations, 1.4D, 1.2D, 1.6L. So those are load combinations, okay? Just to recall, I can open that. So this is not the complete one, but it's okay. For now, I will open it. So you remember that, yeah, these are all basic load combinations for strength design. You remember this, but these are load combinations, okay? Now, we need to check all the load combinations to see what is the critical load, but we also need to do what is called live load pattern. We need to check all the patterns. Very simple example, let's say here. Let's take 3 span, continuous span. Let's say that we are trying to find maximum negative moments for the mid span. For the middle span, we are trying to find maximum negative moments. Then if we put live load on everything, if we put the live load over the entire span, over the entire continuous span, that is not necessarily the combination which is going to give us maximum negative moments at these two supports. See, for example, if you put this way, what will happen? So you're putting something here, you just consider this load. So you're getting something like this. But now, due to bending here, okay, let me draw the bent shape, that may be clear. Now, we applied live load on all the spans, right? So that's going to give us bending moment something like maybe something like that, right? But now, if you remove the live loading on this span itself, if you put only on this span and only on this span, only on the leftmost and rightmost, this is going to bend the beam like okay. In the previous case, where we loaded all the spans, you might think of it like something like that. Okay, but now when you load only these two end spans, it will be something like that. So now you may be maybe something like this, right? So it is not necessary that loading all of the spans is going to give the maximum positive moments and maximum negative moments at every support. The real fact is that it is very hard to say. We have to check all possible, like maybe do alternating, then do alternating only these, then all, then something. Then we have to check all the possibilities before we know for each span which one among them is giving the maximum negative moments at the supports and maximum positive moment at mid span. We don't know beforehand before checking all the load patterns. So that's what is, we will go to the PCA document now. So that's what they will be checking now. So, okay, first we found out what is our critical load combination. So we have live load, we have dead load. Okay. But now what they will be doing. Okay, first thing they did is we have here our column size and beam size. Okay. This is our span. We have our column size, beam size. So everything, all the sides are fixed. So they will do 4 EI by L, but over here, there are at every joint, let's say this, we are looking at position B, there are 1, 2, 3, 4 members attached at that joint. Okay. So when we are doing just now, when we did moment distribution for continuous beam, we had beam, support, beam. But here we have column up and column down. So we will, when we do the relative stiffness for here, we will have the relative stiffness of this beam plus this column plus this beam plus this column. They all will add up to 1. Okay, so just this beam plus this beam will be less than 1. I hope you got what I was saying. Okay, so now they are calculating all of the stiffnesses. Excuse me. So for EC by L for the column, then for this member, okay, distribution factor, stiffness of that guy by sum of all the stiffnesses, right? Then so carryover will always be half. So 1/2 is carried over, that's fine. Then fixed end moments, everything is uniformly distributed. So WL square by 12. Okay, now they will do moment distribution. Okay. So you can see now how they will do it. So first is they applied the full load combination 1.2D plus 1.6L over all of the spans. Okay. So this is just, okay, this part they are just doing the coefficients. So you can see here, joint A, AB, there is only AB. So it is relative stiffness value is 0.13. So that means this upper column plus lower column plus AB, that is 1. Out of that, AB share is only 0.13. Then BA is 0.107. BC is 0.179. You see BA plus BC, you don't get 1 because you have the columns also. Okay, hope you got that. Now, now we have all of the relative stiffness values. Now what they will do is, okay, fixed end moments. This is for this live load pattern, okay? Live load is only on first 2 spans. Then they will get fixed end moments. Then you can see the usual moment distribution method. Okay, you can just check one of them. So fixed end moment is 110.4 on the left, and on this joint negative, positive 39.8, negative blah blah blah. Okay, so what is the distribution here? So you have negative 110.4, positive 39.8. So negative 110.4, positive 39.8, negative 70.6. That means you need to apply positive 70.6. Out of that, 0.107 will go here, 0.179 will go here. So 0.107 of positive 70.6 is 7.55. So he put 7.6 here. Then positive 0.179 of 70.6 is 12.6. So yes, so 12.6 here. Then the carryover, you know, half of this goes here, half of this goes here, half of this, blah, blah, blah. You know this. Then again, we'll see what is the difference here, like this, okay? So finally, we will get all of the moment. So this is for load pattern 1. Then now is load pattern 2. Only leave out the midspan, load alternate span. Then we will have same thing for load pattern 3, only the last 2. Then load pattern 4, then only the middle, load pattern 5, everything. So now do you see, we need to calculate the moments at the supports for all the possible load patterns. Then we will check now. For example, we are looking at joint A, okay? Support A. Which one is giving us the maximum negative moment? Let's see. So for support A, load pattern 1 gave us negative 99.7. Load pattern 2, positive 100.5. 3 gives us 65.3. 4 gives us 65.99. So maximum is 100.5. So we take 100.5. Is it clear? Hopefully this is now it is easy to follow this document. I'm not sure all of you what you're feeling. Okay. Hopefully it is. Then same way we do for all of the supports. So we take maximum. So now we got the envelope of maximum moments. So this up to step 2 is just an adjustment. So we will take a linear interpolation. This is at center line, but we are coming to the face of the column. So we need to subtract out 16 inches is the column. 16 inches is the column width. So if you come to the right by 8 inches, this will drop to 83.5. So okay, so then we have the values for all of these supports. Then mid-span, how do you get? How did they get this 61.6? So we have 83.5, negative 91.9. So you take if you have in the middle, if you have simply supported, then it's WL square by 8, right? WL square by 8. So okay, so that is for case by case. Let's do that. So for example, pattern 1, how did we get 61.1? So for this particular one, we have full dead and live load here. So what is our WL square by 8 value? So W is 1.2 WD plus 1.6, so 2.12, right? 2.12. So here, your span length for span AB, the span length is 25 feet. So 25 feet, if you calculate WL square by 8, what was W? Okay, 2.12. Okay, here is 2.12 and 25 feet. So 2.12 times 25 square by 8, WL square by 8, 165.625. From this, you have to subtract the average of these two. Then you get 61.1. Okay, it's like this. If you know what is the negative moment at the two spans, and for simply supported case, you know that this is WL square by 8. You are simply lifting this end up. You are simply lifting this end up by this value, and you are lifting this end up by this value. So this curve will now just get moved like that. So what is this lift in the center? It's the average lift of these two. So you have to subtract that much from WL square by 8 to get the midspan. So hopefully this is clear to you. Now, that's what they are doing. So what did they get now? So we got all of the maximum moments at all of the subs. Now this moment redistribution. Okay. So, so first we need to calculate the R value. Okay, flexural resistance factor value. This is just scaled with FC prime. Then we are going to calculate. Okay, you can do it by our usual method. So little d is 14 inch and cover 1.5. So for the beam cross section was beam was 12 by 16. So our effective depth is 14 inch, breadth is 12. So how are we doing the moment distribution, the moment redistribution? So first we need to calculate the net tensile strain. Okay, so don't worry about this formula. You can do it by our usual, how we did it in undergrad. So this is our strain, right? 0.0267. So our mu value that we started was 49.3 kPa. So that is for, we are doing negative moment at support D. We are just doing that for example. That's what they are picking, okay? So I think they should have said, okay, yeah, they are just doing, yeah, for negative moment at support D. That's what they are doing first, okay? So your moment is 49.3, right? For this moment, what is the tensile strain in the bottommost rebar? If you don't want to use this formula, just do by the basic way what we did. It's also the same. There's no difference. We can do it very quickly. What do we have here? We have reinforcement here. Effective depth is D is 14. We have 12 inch. We have mu is 49.8. 49.3 kfoot, right? Now, what is the, just do our usual 0.85 FC prime, A times B equals AS times FY. So, we don't know the strain here. So we are, okay, I think this one is starting with row 0. Let's see, just a second. Okay, just one moment. Just Oh, okay. So let's do based on row 0.005. This is, we know, 0.85 FC prime by Fy, beta 1, and 3/8. So we know this is our FC prime for this problem. I think we had 4,000 psi concrete, 60,000 psi steel. Let's go back and check. Yes. So 4 by 60, beta 1 is 0.85, 3 by 8. Okay. So for this, epsilon t will come out exactly 0.005. So just 1 second. Okay, just a second. Okay, let's just solve how much steel we need and do it. So we need 49.3, right? This is our MU. So how much of rho we need? So let's do by both ways. For example, you can take, let's just do from scratch first. 0.85 FC prime A times B is ASFY. Then we have our MU is ASFY times D minus A by 2. So this is 0.85 FC prime A times B times D minus A by 2 is giving us 49.3 kip. So we have times, let's convert to kip inch, times 12 inch kips. This is 854. We have B is 12 inch times A, D is 14 minus A by 2. Now let's solve the quadratic for A. So I hope this part you remember from undergrad. If not, I will quickly go over. So times 12 divided by, so this side we have 14.5 is A times 14 minus A by 2, and 14A minus A squared by 2. So A squared by 2 minus 14A plus 14.5 is 0, or A squared minus 28A plus 29 is 0. So from here we can get our A. You can quickly do it. So
It would be 26.92 and 1.07.
okay, so it is A is 1.07. That is our answer. So now we have C value is A by beta 1. So that is this 1.07 by 0.85, which is 1.26 inch. So now we have, this is 0.003. This is C, that is 1.26. This is D minus C, which is 40 minus 1.26, 12.74. So what is our strain in the steel? Divided by D minus C equals strain in the concrete by C, right? So our strain in the steel is 0.003 by 1.26 times 12.74, which is 0.03. Okay, so 0.03 is the strain at the level of the tension steel. So now let's see their value. Okay. So let's go there. Okay, 0.0267. All right, so they got slightly different. We got 0.03. Okay, so I think it is some approximation somewhere, but it's close. Okay, so if you do by, you can do by flexural resistance factor as well. It will not be that different. Okay. Excuse me. So now this is our, according to, this is just from our elastic analysis, we need this much steel. We need some amount of steel AS, that is according to elastic analysis. Now we can calculate AS from here, right? We know the a small a value, we can get AS, but we don't need to provide that much. We can reduce it. How much? So first iteration. So you see 1000 times epsilon T or 20%, whichever is the least, we can adjust that. So now we will say that, okay, this is 26.7, 1000 times epsilon T or 20, which is smaller, 20%. So now we will reduce our negative moment there by 20%. Okay. Then now we will do it again. Now we will get epsilon T's, of course, it will be higher because moment is smaller. Now we got bigger, again 20. So adjustment is still 20. So that's all. We keep it at, our adjustment is 20%. So like that, by doing at every single support the negative moments, we got for support A, finally we got 17.9% reduction. Support B, we got 15.3 on left side, 20% right side. We got all of these reductions. Okay. Now the engineer can make decision to reduce any negative moment or positive moment based on, okay, there are other things like, okay, uniformity, economical design, new design, detailing, etc. So we have other factors too, but this momentary doing this momentary distribution gives us a big choice to, or it gives us a choice to make a big reduction in the cost, right? So there is 20%, 17, these are big numbers for reducing the amount of steel required. Okay, so That's what is the advantage of moment redistribution. Now you can see that, okay, this is the adjusted moments. So earlier 40.3, now 31.5, earlier 48.1, now 38. You can see positive moments have increased because of the drop in the negative moments, but still overall the adjusted one will require much less steel than the unadjusted one. So that's it. That's the moment redistribution for continuous beams for economy. Now, we have already seen that really if we do it by hand, it's going to be very, very long. For any continuous beam that we have, we cannot do all the load patterns calculation by hand, then get the moment envelopes by hand, then run through the iterations for every support by hand. It's going to be too much. So that's why we are going to use SP beam. So that we will do next time. I checked a few days back, SP beam, SP slab, everything is working, installed in the lab 227. So only thing, maybe if you're at home, I still didn't apply for the remote permission. I will do it today. So next class, we will do the same thing, what we went over in the manual calculation, that example, we will do the same thing, but in the SP slab. So they have shown that also here. So we will do all of that in SP beam software next time. Okay, software is all fixed, working license, everything is fine. So next week we will do this for sure. We will do a few examples. Maybe we will start just from very basic beam, no continuous. then for continuous beam, we will run it without moment redistribution. That's just from elastic analysis design. Then with moment redistribution, then we will compare them, how much economical it is. Okay. Okay.
Dr. Nathan, can I ask you a quick question?
Yes.
In this moment distribution, we were supposed to use the plastic capacity of the sections. Is it right?
Yes. So
Okay.
this is actually what we are unlike in the steel, where we do get an analytical calculation for plastic moments. In the concrete, we are not doing analytical calculation. Code is giving us a kind of approximation of that. That is the choice, reducing either the least of 1000 times epsilon t or 20%. So the dotted one which you see is as if the plastic hinges formed at those locations. Then the negative moments will slightly drop there or stay almost constant, and positive moments will go down. So that drop is what we are, what the code is allowing us. So basically what it's saying is that if we provide the steel according to the solid line, then we will get some maximum load capacity. We will get the same load capacity even with using the dotted line, but after the plastic hinges form.
And for comparing the transition the section, the concrete section that you use that 0.85785 F prime C A B for the formulation. Can you compare these to the to that part that we were talking about, serviceability, and where we are on what points? Because we are supposed to use nonlinear capacity, and we should pass, and our load should be very more than serviceability, but there we are on the curve.
Yes. Okay. So here what we calculated here is just the nominal or design moment capacity. We are just doing according to the equivalent compression block that we use as usual. but we don't know. Over here, we are not worrying about what are the curvatures. So that is, you're right. So we should actually calculate if the plastic hinge forms, then now the maximum deflections are going to increase. So whether that is still in the permissible limit or not, we must calculate. But now there is a difference, because earlier the moment curvature diagrams that we were developing, we are checking for the ductility at the level of a section, But here we are already doing the analysis at the level of a member. Now, the reduction in steel, yes, you are absolutely right. We are doing at sectional level, and we ideally we only can do moment redistribution if plastic hinge can be formed there. How do we actually check whether plastic hinge can be formed there? We need to do our moment curvature relationship. Then we need to see, okay, where is it curving, moment curvature diagram? Okay, do we have enough ductility there? So ideally, if we want to check whether at some particular section, we can assume that plastic hinge is going to form there, then we need to develop the full moment curvature relationship like we used to do. But in the code, they have, since it's very laborious to do for every analysis, they have given us the clause that if our strain is, if our epsilon t is 0.0075 or more, then we can assume that it is good enough for plastic hinge to be formed, and we can go ahead with moment redistribution.
Okay. Can you please go to your PowerPoint?
Yes. Yes.
Here, exactly. This formula, this formula that 49.3 equal to 0.85 F prime CAB. This in which stage we are when we assume this formula?
This is in the stage where concrete is crushing. So concrete strain is 0.003. So if we look at that Hogmestad curve, which is like that, then this is the peak, and this over here, the strain is 0.0038. We are a bit before that at 0.003. So this is usually used for nominal moment capacity in for ACI 318. When we check the nominal moment capacity of section, we always take the ultimate strain concrete to be 0.003. But what we did there, we were going the full all the way. So we did at FC prime, and then beyond also we can do it.
Okay, and my question is, normally service loads should be way lower than design loads with factors.
Yes.
So why in service load we went through that parts that we totally collapse and then go to the nonlinear parts, but here we are before a prime C.
Okay. So this, when we do that one, that was for our moment versus curvature diagram. So we needed the true behavior, like whatever is the moment versus okay, how is it going to look? Something like that. So we needed this true behavior, but there we are only concerned with what is the strength of the section. We are not concerned here with whatever loads are being applied. Of course, if we want to look at deflections, then we will use only service loads. But if we want to look at plastic hinge formation, we have to look at ultimate load, like failure and beyond failure also, to see after it fails still how much ductility it has. So So what we did at that time is purely with analysis with respect to strength. We are not looking at only strength of the section versus curvature. We are not looking at load being applied externally. That is for moment curvature. But for serviceability, we were looking purely at service loads. You are right. So service loads on the moment curvature diagram, they will hardly be maybe only somewhere in this region. They will not come even close to anywhere near the ultimate strength. But it is still nonlinear. Even in that region, it is already nonlinear. See, that is nonlinear because for serviceability, what we are taking is okay, I think I know where the confusion is coming. For serviceability calculation, the nonlinearity is coming from where? Nonlinearity is coming from, so WL, let's say simply supported 5 by 384 WL power 4 by 384 EI, right? So this I, the more you load, the more it cracks, and some part is cracked and some part is uncracked. So the effective moment of inertia is continuously changing. That's why this moment versus deflection, this curve was nonlinear because of that. But the moment curvature, we are not talking at the member level at all. We are only talking at the section level. For moment curvature diagram, we are only dealing with section level. So we will do everything. It is cracked, uncracked. We assume, we don't assume anything. We calculate exactly according to this section. But for the moment versus deflection, for the calculating deflections, our effective moment of inertia is assuming some average of between uncracked and cracked sections. Those calculations were for a member. These moment curvature.
It means we are, depends on other sections of the beams as well. Yes, right, just not the weakest part of that.
Yes. We are doing some kind of averaging over the entire length of the beam.
I got it. Thank you so much.
Sure. Okay, I will go for something, but we will for sure do the moment redistribution in the software. Also, if there is any, for some people, maybe it will be for many years, and we can redo this part very quickly. Yeah, okay, we will do next class. Thank you. Yes. Thank you. See you next class. Go ahead.
All right. Thank you, Dr. Nathan.
Yes.